And what the review guide is the bullet point list of everything that I have been taught you over these first 4 weeks and everything I expect you to know. So there's some stuff we cover that I just mentioned that you don't necessarily need to know, but if it's on here, you do need to know it, and it can be on the exam. There's no way that I can ever put all of this material on the exam. It would be like 20 pages. So I'm going to pick sort of the major parts of it. But invariably, there's always that one thing that you never really get to learn, and then that's the one thing that always ends up on the exam, and that's just how the kernel works. So the way that you want to use this is to go down the list and ask yourself, like, do I understand what this bullet means? If I was asked a question about this, would I be able to answer it? If it's something that says calculate, would I be able to do the calculation? And the key and the sort of the verbs on here are the important part. So when I say describe, that means use words, give me a description, kind of give me a couple sentences about something. If it says sort of use a data sheet to identify something, that means take the data sheet and look up some parameter. Tell me what that parameter is. If I want to say contrast CPUs for embedded systems, that's tell me what the difference between these CPUs are. Why are they different? What's going on? So the words in here are of a specific nature. Like I'm not randomly picking my words. So assignment 1, calculate the address of a memory mapped register. So one question I could ask is, what is the address of port E's D-out register in the GPIO? So you have to look up the base address, you have to look up the offset, add them together, and that would be its address. Now, I know you just finished up on Lab 2, and your brain is all about Lab 2. So what I want you to do is I want you to pull this up on Schoology. It's on the underneath the exams folder. I want you to take seriously like 3, 4, 5. We're going to take 5 minutes to do this. Like, look through this list and write down any one of these that you don't understand. And I will stand here for the rest of class, and I will answer your questions. I will show you where that material is in the notes. I will talk to you about what that means. Once you stop that, I have an assignment that deals with the UART. That assignment is not due until you get back. Well, it's going to be due right there on that Wednesday when you get back. So unless we're going to sit, we need to talk about the exam for a while, and we spend all day talking about the exam, but there is work that you can do for going forward. So let's take a couple minutes, look at this, and come up with questions. That is something that you will see on the UART in the sense of it has a status register and an interrupt register. The status register is kept up to date, but the interrupt register always stays the same. So there's an interrupt flag that says I'm done sending. And if you never ever clear it, it's always going to say I'm done sending, even if you've sent 15 things. Whereas the status register might itself clear. But the main point here is active goes to pending when an event occurs, gets selected for service by the processor based solely upon priority. If you are executing and someone with a higher priority comes up, you get bumped to preemption, and you only return to active once that higher priority interrupt finishes. So Kevin's question, nested is talking about this preemption model, and vector is talking about the table. Vector is talking about this table where all the interrupts are stored, because they are pointers, they are vectors. All right, other questions? Yeah.
On the topic of interrupts, what's the difference between edge triggered versus non-edge
Okay? An edge triggered interrupt occurs on a positive or falling, a rising or falling edge. There has to be an edge. A level triggered interrupt is triggered simply on the level of the data. So either it's high or low. So if you had, we have space here. So if it was an edge triggered interrupt, you will trigger on a positive edge or a falling edge. A level triggered interrupt, let's say if the level triggered interrupt will simply trigger if the signal is low or high. It doesn't need to see an edge.
But functionally, how does that play out? Is different.
Because this will always trigger for as long as this is low. So this will trigger on this instance, but as long as this signal is low, this will continue to trigger. So usually this occurs with like the reset button on a processor. As long as I hold down that reset button, reset, 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 reset. Also, if something goes high, if something's in a low power mode, that high signal can kind of charge a little bit of the circuitry and make it turn back on. So level sort of triggered interrupts. And as long as it's at that level, it occurs. So an edge is sort of an instantaneous thing. You're going to get one. Level is you're going to get sort of continuous interrupts. So you get one here, and you get one here. You really don't use level triggered interrupts. Well, at least I haven't. But that's what the difference is. Other questions? Kyle, what questions do you have?
For like when you're could we like just do a problem of mathematically calculating the address of like a memory map register?
Okay. So I'm going to pick a random register off the top of my head, and we're going to do it. So let's look at the status register. So let's say I gave you a problem. Let's look at the status register of USART 0. I'm just making this up as I go. Okay? So the address of any register is equal to sort of the peripheral's base address plus the register's offset. Okay? So you've got to look up two things. You've got to look up what peripheral am I in, what's its base address, and for this register, what's its actual offset. So for this device, we're talking about USART 0. And so what you need to do is you need to go into the reference manual. And I think in the first table, it has the base address of all the peripherals. So let me pull up the reference manual. So you will have the reference manual. The reference manual is your friend. And if we go, let's see. It is here in chapter 5 where it is sort of the memory and bus system. So you've got your core peripherals here, you've got your low energy peripherals here, and we are looking at USART 0. So USART 0 in this context, the base address is 4000 C1000, however you want to describe that in hex. So I'm going to say my base address here is hex 4000 C000. Okay, that's the base address of my peripheral. Now that you know where the peripheral is, and all the peripherals of that type are organized the same. So even though you have 1, 2, 3 USARTs, they're all organized exactly the same. So you're not going to find a different. Keep dropping. You're not going to find a different table for this guy, this guy, this guy, because they're all organized the same. So what you do is you come down to chapter 17, which is the USART, and you come down here to the register map, and you say to yourself, well, I want the status register. And you can see here in the corner that the status register, its offset is hex 10. So I'm going to take 4000 C1000 plus 0x10, and I'm going to add those two numbers together. And that's my address. Let's make sure we get that. So you see, it's the peripheral's base address, which you look up in chapter 5. You have to go to the table in chapter 5 and say, gosh, what is this peripheral's base address? The base address is the lower number. Then you have to figure out for that peripheral, what is the offset of that register. So this is 4000, C1000. We looked that up from chapter 5, and then we went to the peripheral, and we found that status was offset by 10, and you just add the two together. That's it. You should have done this in assignment 1 and lab 1, where you manually sort of stitch those things together. Does that answer your question, Kyle? It's always the same process. It's always base address and register offset. Base address you have to look up, offset you have to look up. Now, and I would trust these offsets here, because sometimes in the definition itself, there are other offsets, that, like where the register is actually defined, but this is the one, these are the ones right there that you want, those offsets. Kira.
Are we allowed to use the calculator? That was a really easy addition, but sometimes the hex code.
Let me see how I can say this. You are allowed to bring your calculator, so bring a calculator. Sure, I don't see why you can't use the onboard Windows calculator. So you can bring your own TI 89, 85, 84, whatever. That's fine. And yes, if you wish to use sort of the Windows calculator, you can. I will say that there is not going to be a ton. I'm not testing you on binary to hex conversion necessarily. But you can use it. Sure, why not?
That's what he said in the article that
What was he testing you on?
Well, he had said something about difficult binary.
Yeah, you've gone through 220 and you've gone through 260, so I'm confident you've learned it once. I don't need to keep. Take it out of your man's binary hex conversion. You can do that. You can work for Google, right? So, I expect you to know it. I am not going to grind you on that. Like, I need you to know, if you look at the questions, they're conceptual sort of things. Mike, do you have a question?
Would you like a Wi-Fi video, for example?
Okay, that's a good question. So, do you want me to do it from like a mask? Okay. Let me do this as well. Let's stay on this. Let me pick a register here just so we can have something to talk about. So let's look at this frame register right here. Okay. So let me get rid of this. The key things that you have to determine are, what is the width of the field that you are dealing with? And the width of the field is dictated by the layout of the register. So let's say that I wanted to set parity. Parity is 2 bits. So that means I need to mask and save 2 bits. Where did I lose marker? They're all in my pocket. So in any sort of bit mask operation, the idea is that you're going to have a pointer to something, right? You've got some sort of address that you care about. You are then going to take that address and you're going to AND it with some sort of mask. The purpose of the mask is to clear the bits you want to modify, and save all the others. So this guy's job is to clear bits and sort of save the others. Okay? So the idea is that when we come over here, we're going to clear these 2 bits. And you need to clear those 2 bits because you're going to do an OR operation to write to that register. If there is a 1 already in that bit field, you will not change the bit to a 0 if that's what you want, because anything ORed with 0 is anything. Yes? Yes, because anything ORed with 1 is 1. So, the idea is that this part of it clears your field. Then you're going to OR it with some sort of value. And I'm going to leave it broken down like this. So this is at the very base level. So if we were doing this problem here and we were going to modify parity, parity is bits 8 and 9. So I'll do sort of 9 and 8. And let's say that the value we want to put in there is the binary value 1 because you've looked at the table and that's what you've wanted to put in was the binary value of 1. So you're going to put in this value, but you're also going to shift it over to the position that you want. And the reason that you want to do it is that if you just ORed this register with 2, or with the value 1, and didn't do anything, you would set this bit here. So you need to slide these bits over into this position. And the reason I talk about the mask is that the mask has to specify 1 1 1 1 1 1 1 1 1 1 1 1 1 0 0 1 1 1 1 1 1 1 to do that specifically. So if you write the mask out explicitly, I mean, gosh, this would have to be, let's see, that's 4. Oh, that one's really terrible. So you would have to write this mask out as like F, 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 and then the ninth bit is 0, so that would be E. Then those are 9 and 8, so this would be C, like F, F. Like you'd have to write this mask particularly such that it directly corresponds with these bits, and that's really, really, really annoying. So what we've done in class is we said, you want to destroy a 2-bit field. And so a 2-bit field is binary 3, because hex 3 is 1 1 in binary. And what you're going to do is you're going to shift this over to the same position as the field, and you're going to invert it. So what that does is that takes 2 bits all the way to here, and these are now 1s and 0s. When you invert it, these all become 1s and these become 0s, and it destroys this field and saves the others. So if you were going to set the status value, or the status the stop bits field to 1, your code would look like that. So you'd have to say it's a 2-bit field, it's 8 bits over, this is my value that I want to write in 8 bits over. This is a sort of a not great example because, or maybe it's a harder example because that field is in a weird position. Let's look at it if I was doing, if I was changing the data bits. So if I was going to change data bits, I would take the address, and if I was going to write this out all manually, it'd be 0x1 2 3 4 1 2 3 4. So you see how I'm going to put a bunch of 1s all the way through here, and then these are going to be 0. So it's going to kill that field. And if I wanted to write in 3 into that field, I could just write in 3. So what this line of code here does will set data bits to hex 3. So this will set data bits to hex 3. This will set parity to hex 1. Travis, yeah.
Could we, it's kind of handy, could we use 0xf as the mask in this case since there are no values in bit positions 10 and 11?
If you use just f, it would sign extend it. It would sign extend this with 0s, and it would kill the bits above it.
I was talking about, sorry, with the parity mask. 0x3.
You could, but in the future, maybe some other bits go there, and now you've broken it. So you want, and I've seen, in looking at your code, I've seen some people do that. They go, oh, this is full of nothing. Let me just override it. Like, really be careful about that. Because, like, maybe, yes, for this process, there's nothing there, it's never going to change. But if you get in the habit of just assuming that some field doesn't get changed, and you then one day move to another process, your code's going to break, you're going to have no idea why. Ben?
How should we treat the timer stop and stop? Like, should we clear the stop bit?
No. So the timer stop bit is a write-only field. So you do not clear it. You explicitly start the timer, and you explicitly stop the timer. You have to... The device doesn't register clears. Like writing a 0, it can't detect. It doesn't do anything for. So on the timer, let me find the timer. So if I come down here to the register map on the timer, like this is, you see this W mean? That means it's a write-only register. And I'm looking at it now, and I'm looking at write 1, and it maybe means it only understands like physically writing a 1. Because it's write only, you cannot read these and like get the state of the timer. So you have to write a 1 here to make it start. You have to write a 1 here to make it stop. So when looking at some people's code, when they started the timer, they would say timer 1 command equals 1 to start it. And they'd say timer command equals 2 to stop it. Which will technically work, but you really, if there are multiple fields in a register, you should always use the bitwise OR operations. You shouldn't write to it directly. If there is only one lonely field in there, fine, use the equal sign. But if there are multiple fields, you don't want to use an equal sign. Michael, question?
Yes, you were setting the data bits to 0x3.
Yeah.
Would that be the same as masking it on 0x?
Okay, so let me see what you've got as a not. Yes. Yes, it would. Because this would become a 0, the rest would become 1s. So if you were, like in the read modify function, right, that we have, you would, if you were going to modify data bits, you'd say modify data bits, and then you'd put F for the mask, because it's 4 wide. You'd put 0 for the position, because it's in the 0th position, and then you'd put the value you want. So this would become 0xf over by 0, and then this would be 0x3 over by 0 as well. So, and this is what I've been kind of saying since the first lecture. Like, this is day one how I taught you how to do this, because it's sort of easier to do that. But this cannot be turned into an algorithm. This can be turned into an algorithm. That's where your read bit field function comes from. And so hopefully you're using the heck out of that function to change all of these configuration bits rather than writing out these long strings of things over and over and over again. Like if you're doing this, you're just going to be introducing errors, and it's going to make your life tough. Okay, to answer your questions on this. To answer your question on the timer.
So using the read modifying rate, you can't really read the value, so
It's a modified bit field function. What's your question, Ben?
I feel like you can't really specifically modify one bit since you can't read the other one.
Yeah, you can. I can OR this with binary 1, and I can OR this with binary 2.
Oh, okay.
And that all that does, because whatever might be here, OR it with 0, it just stays there.
Okay.
So the way in my code, hang on a minute. So in my code, it's timer 0 command, and then it's OR equals 1 for start, or it's OR equals 2 for stop. So, you can't read these. There's a write-only register. You can't read this register. If you want to know whether the timer is running, use this running bit in status. Don't look to this command. The command registers, and especially in the UART and other devices, are always going to be write only. Another thing is don't trust peripheral logic to save the state of your program. So in a couple Lab 2 solutions I saw, people were saying, was my light on or off? Well, let me go ask the light whether it's on or off. I would use an internal variable to keep track of that rather than to jumping out to the GPIO and then changing it, because other functions, other programs might be able to change that GPIO. Maybe you forgot about it. You need to keep track. Don't use the peripheral's internal state to keep track of your own state. If it has a status register, if it's got a flag register, great. That's what it's used for. But don't kind of look at something's configuration and necessarily tell what you should do. Keep track of your own state and your own variables. Other questions? Felix, you had a list. What's on yours?
So defining or distinguishing the difference between exceptions and errors.
Okay, so I mentioned that really quickly. If you look on this slide here, exceptions come from the processor. They have negative IRQ numbers. Exceptions are generally bad things. So if you look at the exceptions, you've got a system call, you've got a usage fault, you've got a bus fault, you've got a memory management fault. So exceptions are not that they're errors, but they're normally, I'm just going to say bad things. We'll just call it that. And they come from the processor. That's the main distinction, is that they originate in the processor. Your interrupts down here all come from your peripherals. So everything with a 0 or positive IRQ number, so everything with a 0 or positive IRQ number comes from a peripheral. And the reason for that is that ARM makes this processor. So the ARM is going to say, we reserve all the interrupts from here down for our own usage. And then we're going to start here at 0 and let you go up and let you define all the interrupts you want. Because ARM just sells you the core, and Silicon Labs takes it and then adds on all the peripherals. So ARM is just leaving space for IRQ 0, IRQ 1, all that stuff. Negative interrupt number comes from the processor. Main difference. Darren, what questions do you have?
Let's talk about bit banding.
Bit banding. All right, let me find a friend bit banding. So the main point of bit banding is that when you modify a register, it goes out to memory, it looks it up, it talks to it. It's kind of a long process. So it's a read from a memory address. It pulls that memory address from the processor, you muck with it, and then you write it back. That can take some finite amount of time. And so in that amount of time, maybe that register has changed. Maybe someone else has changed it. So what bit banding does is it allows you to access the same register but in a different memory region, and it guarantees that your operation will be atomic, meaning that nothing will interrupt it. So if you're going to change the UART's configuration and you do it in a bit banding region, nothing will happen to that register until you're done writing to it. So the idea is that it's a different bus, it's a little bit faster. Yeah, that's the main thing. It's atomic. It's that the operations on the memory mapped register are atomic. Ben. Yep, the bit bandage. So basically, they've copied the entire memory region into another region, and it's just offset. So let's see if I got a picture in here. I don't. Let me pull up the reference handle. All they've done is they've just copied the memory into a different region. So you see here how here's like SRAM data space. Here's SRAM where it's bit banded. So if you were having a lot of contention on the bus, and there's also the dedicated bus to talk to RAM, you could reorg your programs to go here. So you could copy your entire program up to here, and then re-begin execution here. And that would do it. The same thing with the peripherals. The peripherals generally live in here, and if you wanted to access them through bit banding, they live now up here. So you kind of take all the addresses and you add like 200,000 to them, and boop, there you are. That's how you talk to them over the different addresses. You get to the same place. It's like going on the toll road versus going on the regular highway. You have to sort of go a different route, but you get there a little faster. Ben, yeah. It's an extra complication. You've got to write more software, and you got to figure out whether I'm doing peripherals or what. Because this is the natural mapping, right? If you then want to map it here, you've got to now change all these data structures that you've got, and maybe you don't want to access them all through bit banding. It's just an extra complication. You may not even want to deal with it. Like for our applications, we really don't need to deal with it. So it's a neat little feature, but you don't necessarily have to want to use it. It's there if you need it. Jason, what's your question?
And you use the bit banding field for like the SRAM or peripheral, and you're saying that your bus is in the flowers.
If the bus is busy, or if you want to, let me pull this up. Like, if for some reason the bus is busy, or you don't want to access everything, because kind of naturally everything comes across the system bus, and you can get your instructions and your data off on different buses if you want to, but they got to be moved to another region. It's just if you're having performance issues because you're having so much traffic across your peripheral buses that you want to make sure that you get a good connection to them, maybe you go a little faster. It's there. I have it in here so you know about it. Whether you necessarily always need it is sort of a separate thing. The one thing they put, the two kind of reasons they put here is, one, the read, write back, bit shifting and masking. If you do it as an atomic operation, you can potentially reduce your code size. So you're just writing a value to this one place. I guess you can reduce code size. I don't know if I necessarily buy that, but some of my students in my embedded systems have written a ton of code for their Fitbits, and they have run out of program memory. And so maybe if you're on a really constrained platform and you run out of program memory, you take this kind of optimization. And so that would make it faster because it's a smaller program size. The other optimization that they talk about is that it's atomic. And the atomic is, if for some reason you had multiple things writing to a peripheral, which I can't really see why you would, but you wanted to make sure that you won and that you talked to it on the right address, that's what it would do. There was another hand over here. objects into other region of code that give you a special ability. Now, I guess, let me clarify what I say. Now, whether you actually move the code or begin executing in that extra region, let me clarify this. This is probably still, I begin executing in here, not that I physically move it. Let me clarify mine. If I ask you about bit banding, Travis, you're going to say, oh, it gives you atomic read-write authorizations and it gives you a dedicated path to the peripheral. That's what I want to hear. That's all I want to hear. That's all I want to hear. If that makes people better. Other questions? Kira, do you have any questions? Okay, so what bullet's that? Okay, so this is in lecture, so always think of these questions in context of lecture. This is in context of lecture 1 where we're looking at the different processors. You have a 32-bit processor. That means it has 32-bit word size and 32-bit data size. So all of your instructions live in memory and they can be 32 bits long. All of your registers here are 32 bits wide. Because when we look at all the registers here are 32 bits that you can write to. If you were using, this processor, this is a Atmel 328P. This is a 16-bit processor, which means 16-bit word size, 16-bit data size. The Sleepy V here is an Intel 8051. It's an 8-bit processor. So 8-bit instruction size, 8-bit data size. So the difference with the data size is kind of how big are your operations. So doing 32-bit additions on your Gecko, no big deal, because all of your registers in your ALU are 32 bits wide. Doing a 32-bit operation, 32-bit addition, so adding like 4 billion to 4 billion on this 8051 is going to require multiple instruction cycles. And multiple instructions because it can't natively add numbers that large. So that implies, so the longer instruction word size implies the size of the operands that you can work on, and implies kind of also the number of instructions. I got 32 bits to encode all my instructions. I'm going to have the Gecko does, I'm going to have way more instructions than a 16-bit or an 8-bit processor. So if you think back to 260, when you were looking at MIPS, you had a certain number of bits that told you what instruction this is. If I have 32 bits versus 8 bits, I got more bits. I can do more stuff. So that's sort of the main thing there, is comparing and contrasting just those two systems. So let me look at lecture 1. So it's kind of very specifically what I'm talking about is basically this table right here. And this is, the 328 or the 328P is an 8-bit system. Nothing's really a 16-bit system. But they naturally let you have 16-bit words in the programming language. So this is what I'm talking. I'm talking about really kind of like this line right here. Like your Gecko's 32. These are 8-bit. Cheaper, smaller, lower power. That's the difference. So there could be a question of, you need to build a key fob for a car, right? To lock and unlock your car. It needs to do just really stupid stuff, and it needs to last forever. Are you going to use an 8-bit system, 32-bit system? 8-bit system is going to be a little cheaper. This Sleepy Bee is 93 cents. The Uno, the board itself, is $2. They're lower power. If you look at, do I have watts on here? No, I don't have watts on here. They're going to be lower power. They're going to be older. They're going to be older. I should put watts on there. That's a good one. They're an older chip. They're just going to use less power. Travis, what questions do you have?
I guess going over the reviewing passing by value, pointer, and reference, more specifically the difference between passing by pointer and passing by reference. Let's just kind of review that.
When you have a function and you pass by value, you copy the value into the stack and into the function parameter, and you actually make a copy of the object. So pass by value is really bad because if you're passing, let's say, a large object into a function, it can blow up the stack because it runs out of space. I found that out the hard way my senior year in embedded systems class, where I was trying to manage a lot of UART data coming into my processor. I had an interrupt handler that would take a pointer to my UART buffer and would then read from that buffer. I made the buffer pretty long because, well, I wanted to hold a lot of data. I thought I was passing a pointer. I was passing the entire array. So every time my interrupt handler got called, it would copy the entire array onto the stack. My stack would blow up. My processor would reset. And I could not figure out why. It would run, it would run, it would run. And as soon as it received data, it would reset. So pass by value, except for sort of single word parameters, so ints, chars, things like that, you want to use pass by pointer. The difference between pass by pointer and pass by reference is honestly, they're the exact same mechanism because you're passing a handle to the object. The pointer is just more clear in that it explicit when you type it in the calling function, it looks like a pointer, and you know it's a pointer, whereas if you put it in the calling function, it can look just like the object. Both are passing a handle to it. The one you want to always use is pass by pointer because it's explicit what you're passing to the object. There's probably a deeper technical details you can pass by reference and pass by pointer. And Dr. Hoovermeyer would know. But the main thing is value is a copy. Value actually copies the data structure on the stack. Reference and pointer give you handles to the object. You just always want to use pass by pointer. And I'm trying to think of like when it's ever good to pass by reference. And I never think it is because I think it always looks too much like pass by value. And so I wouldn't use it.
Maybe there were hearing what the difference was.
And I can't remember the difference is. For this class, the difference is not that important. Just pass by pointer. Pass things by pointer. You have to reference an object to get its pointer, but you pass that pointer into the function. Joe, questions?
When you say describe how timers can be used to generate pulse width calculations, that's similar to what we did in lab 2. So instead of turning on the turning on output.
Similar, yeah. So there's that. There's also, if you go to the timer left, I mean that would be one way, yes, is that you could instead of turning on an LED, if you're toggling a pin, that would generate a pulse width modulated wave. At the same time, pulse width is not necessarily always a square wave. So let's say if you wanted to make a faster wave, what would you change in that timer based on how you kind of did lab 2? Right, so if you wanted that timer to pop faster, you would lower top. And if you wanted that wave to be longer, you'd raise top. So that is one way to generate a PWM signal with a timer. Another way to do it is with this sort of capture and compare system that the timer has. So remember that you set a threshold here, and that until it counts up to that threshold, it's high, and then it becomes low until it hits top. So the way that this one works is that it'll make it 1, 2, 3, high for 3 cycles and low for 2. And it's based upon the capture value and the top value. So the top value resets the timer, and the capture value tells it when to go low. So those are 2 methods that you can use to do PWM. If I ask you, describe a way to generate a PWM signal, you can give me either response. You can give me what Joe said and say, look, I would vary the top value to change the frequency of the wave. You could also say, I would use the top value and sort of the capture compare value, and that would also generate your square wave. However you want to handle it. The key of that question is understanding what PWM means. The PWM is a square wave of varying duty cycle, and understanding that a timer gives you some amount of time, and you can hit the top value, and it can reset and you do stuff. Just explain that. Matt.
Why would we use volatile for a million math?
All right, so for this sort of surrounding the discussion of bit banding, a couple things can occur. The volatile, let me pull this up the slide. Volatile tells the compiler that the value you are about to read can change. And the reason to use volatile, is to make sure that it doesn't cache. I'm trying to find this. I don't have the volatile keyword. The reason that you use volatile is to make sure that it doesn't cache your value. So here's the thing. Let's say you're doing something like you were in lab, where you've got multiple interrupts kind of modifying different peripherals. Right? You're running in main, you're getting ready to change your timer. Boom, interrupt occurs, changes the value of some register. So let's say you read the status register of the UART. You're in main. Boom, interrupt happens, something else happens, that value changes. When you then go to modify it or read it again, it's going to use that cached internal value in the processor. And it's not going to go back out and look up and see if it's changed. So volatile, if you're modifying things in a loop, especially in a loop, the compiler is going to go, oh, I'm going to save you time. I'm only going to read that variable once. And it's going to cache it, because it's going to assume it's not going to change unless you write back to it. So volatile says, every time you read this pointer, actually do a read. Like, actually do a read and don't use a cached value. Because it implies that that value can change, that someone else can change it. So that situation can occur with if multiple things are writing to a peripheral and you're reading from it, the fundamental thing is you're trying to prevent the compiler from only reading your variable once to be smart. Because it's going to try to save those reads to make sure that you don't do it multiple times. Yeah, so here's my sort of note on this. You've got to use the volatile keyword, and it's to prevent the compiler from optimizing your code away and only reading some value once. Here, you're not really turning on any compiler optimizations. I think the default just compile optimize 0. But future optimizations are going to try to be really smart and really sneaky, and it's going to look at code and go, oh, you never read that value. Delete. It's just going to knock out the code. So that's why in the while loop that you have at the bottom of your programs, I actually put an operation in there to increment a value, because I'm always kind of concerned what the compiler is going to do when I get into my program. So I was writing assignment 3 last night, and I put a breakpoint on my last line of code, and I go to run it, and I go, well, this is wrong. It tells me everything is 0. And what was happening is that I think the compiler was automatically jumping me past main. Like, it would say, oh, you're in that while loop, and that while loop does nothing, so I'm just going to go ahead and reset. Once you leave main, the processor resets. So you want to be careful setting breakpoints, because it's not guaranteed that your breakpoint is actually on that line of code. And it's for those kind of reasons that you use volatile and you do the funny things I do with the while loop to make sure that your important code is not optimized that way. Okay. Michael, Dan, Travis, Russell, questions?
Just a simple one. When you say describe the organization of GPIO and packet, do you mean physical or do you mean like memory?
I kind of mean both. So something I would mean is there are 5 different ports. They're called A, B, C, D, E. Each port lives in the GPIO address. There are 16 pins on a port. They can all be configured to be inputs and outputs. They can all have different functionality. What is the general organization of the GPIO? There's 5 of them. Each of them's got 16 pins. They all support different kinds of interrupts. That's what I'd be looking for that kind of question. Michael.
Like the timer calculations, the maximum count time and the fastest flow rate.
Yes. So if you look at your timers, so one thing I will say is you're not going to have your notes. So let me go here. You're not going to have your notes. So any sort of equation that I've come up with, you're not going to have. Now, if there are equations in the reference manual and the data sheet, you'll have those. You'll need to remember where to have them. But here's the idea: is that for a counter, let's invert the proper statement. The maximum amount of time that you can count is the maximum value divided by how fast or how slow you count. So, in general, the maximum amount of time for a timer is max value over count frequency. No, go. Questions?
So you just look up how many bits the timer is and operate frequency?
Yes. So this value here, max value, if it's a 16-bit timer, 2 to the 16. That's how many values you can do, 65,536. Divided by the count frequency. Now, the count frequency is not necessarily just a bus. Remember, it's divided by a prescaler. So if you look here on the next slide, it's maximum value divided by the frequency, but the frequency gets divided by a prescaler. Because the bus, that high frequency peripheral bus is 14 megahertz. You're not going to be necessarily running at 14 megahertz. Or 25, for this example, it's 25 megahertz, whatever it might be. So 2 to the 16 divided by the frequency divided by how much the prescaler is. So if you configure this 16-bit timer in this manner, it can count a maximum of 1.32 seconds. Kind of inverting the problem, like how do we make it do a square wave? If I take that equation, that time equation, because that's a period, and I invert it, like I just do the inverse of it, because inverted period is frequency, I get this equation. It's the exact same equation I have on the other side. I've just inverted it to talk about frequency. So you can plug in the same values of, well, what's my frequency source, what's my p-value, what's my maximum value, and that will give you the maximum frequency. This actually gets you frequency over 2, because, as I said, you're taking the entire duration of the timer and making it pop. So, however fast you can do this, you're going to do it for one part of the edge and the other part of the edge. So, you need to make sure that, sort of for maximum frequency, you need to make sure that 2 of those periods elapse. So, this is sort of the final equation here of, if I have a timer, the frequency that I get out of this timer is based upon these values. So let's keep going backwards and backwards. If the question is what's the maximum frequency, how do I change these parameters to maximize my frequency? You want to make the denominator as big as possible and the numerator as small as possible. So you want the fastest clock you can get, you want the slowest prescaler you can get, and you want the smallest value you can get. So basically the maximum square wave, the maximum frequency of the square wave, is every time the timer hits 1, you're resetting. 1, reset, 1, reset, 1, reset. And that's as fast as you can toggle that GPIO. Now, whether or not you can actually respond that fast is a different sort of question, but that's the maximum thing that you can generate, is make your timer run as absolutely god as fast as possible, and then every time it hits 1, reset, toggle, and that will generate the fastest square wave possible. You can also sort of use this equation and say, I want to generate a 50 hertz wave. What is sort of what is my top value that I put in? So if every time the interrupt handler popped, you want to generate a wave of a certain frequency, you need to pick the right top value, and this is how you calculate that top value. So to answer your question, like how do I get the max square wave? These slides right here. You can memorize this if you want, but the thing that you need to keep in your head is the period of the timer is the value divided by how fast it counts. So it's the maximum value divided by the clock frequency divided by the prescaler. And if you stay there, it's
2 to the n.
yeah. So the prescaler is going to be you have those prescale bits, and you can look up in the data sheet like I can divide it by 1 or I can divide it up to 1024. If you keep this equation in your head, you can derive the rest of this. You can work through it. It's not that bad. Because it's like, what am I counting up to divided by how fast do I actually count? That's the fundamental principle, and you can look up those values and you can do them. You're going to have the full period for the exam. You're going to have the full 2.5 hours, however long we have. I think it's 10 questions. So we'll have it printed so it is either 10. It's 9 or 10 questions. It's not 30 questions. Like, you've got a good amount of time for everything. Some of them are quick, some of them are longer response. There's a nice bonus on there. That's what you got. Jason, Kevin, Kyle, questions? Ben.
How do we look at the map file when determining breakouts?
All right. Let me open up the program here. So the map file tells you. So this is my implementation of the. So this here is my implementation of the lab or the assignment that you got. If you go here in the debug folder and you go down to map. Let me open this in something else. Please be sublime text. Not really. If you come down here to map, it is going to tell you where everything in your code went. So you can see from the startup file that this tells you that the reset handler is at 1 AC. And then that all of these other handlers are at 1 DC. So you can look at the map file and you can figure out where all of your interrupts actually get mapped. So as a comparison, let me load up lab 2. And if we look at the map file here, where is timer? My interrupt handler should be at a different location. Where's timer 0? Yeah, you can see that the timer interrupt handler gets placed at a different location in memory. And because it is not mapped, all of these here are mapped to the default interrupt handler, which is at 1D8. here you can look at it and you can see where things actually get mapped. Now here's the difference. The map file tells you where things get mapped. What I talked about here is that if you look at the binary of your program, if you look at the memory map, the first program memory address 0 is the stack point. Program memory address 4 begins the interrupt table. So this is an interrupt, 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 on and on and on. So you can read down this binary, and one thing you can say to yourself is that if these are all the same, they're all going to be the default handler. They're all going to be bogus. But if one of these happens to have a special number, that means he's implemented. And so you can figure out his address, and you can count down the table and figure out who it is, because the table has a fixed order. That's how you can figure out from the binary what interrupts are enabled and where they are. Okay? Your exam is on Monday. I am here the rest of the week. I get on a plane Saturday. You have no work due to me until break. We're not going to have, you're not going to have class Wednesday. We're not going to meet. You do have an assignment due when you get back Wednesday from break. If you want, the assignment I've given to you, you can complete in about an hour next Wednesday. You can come in, do it, submit it, knock it out, get out of here. What you're going to do is you're going to take your gecko and you're going to make it talk to itself. And I have laid out each line of code that you need to follow. I put comments there. Let me just show you. I put comments there, and you can just follow it through. So what your assignment 3 is, basically to take your gecko and tie the transmit pin and the receive pin of USART1 together. What I've got up here is a collection of wires of various lengths. So I used to have a big box of, I'll call female wires, and you can immediately loop things back, but someone has taken my box. So what I have is in some of these, I'll say male, female wire, and other wire that you can connect both pins and then tie the wires together and they'll work. And I'll get the little wire and I'll put it up here. But the basic idea is that you take your gecko, and you take one of these wires, and you physically tie the two pins together. And what you're going to do is you're going to send a single packet, and you're going to make sure that you receive it. You're going to send 2 packets at the same time, make sure you receive them. That's it. That's sort of the lab for that. Or the assignment for that. I had a much longer UART lab that I did last year, but I think I'm going to replace that with an I2C lab, because I think that's more useful. So what you've got under your assignment is here. You need to, every one of these blocks, I've got a little blank space under here where you can write your code. So when I tell you everything you need to follow, this is walking through all of the steps for the USART from the lecture notes that you need to configure. Each one of these blocks is 1 or 2 lines of code. What you're going to do down here is you're going to, task 1 is to send yourself a byte and then receive the byte. That's all you do. You come up with a random number, you send it, you wait for the data to become available, and you read it back out. Don't change these variable names, because I've written a little block of code here that just tests to make sure whether it works. And I'm just going to basically run your program, and at the end, there's going to be a flag called assignment 3 success. And if that's true, congrats, you passed assignment 3. So don't modify these because it makes my grading a little bit easier, it makes your life easier. For the second assignment, or the second task, you are going to send 2 packets at the same time. So remember that there is a 2-level FIFO, and for both transmitting and receiving. So to write to that, you write to data, and then you write to TX data, and then you write to TX double. So you put one here in the FIFO, the other here in the FIFO, they both go out. You then need to wait until the receive FIFO is full, because you're going to receive 2. If you wait until data is available, you will read too early, and you may miss the second packet. So you're going to read the 2 values back in, and if the 2 values that you read are the ones that you sent, and they're in the right order, congrats. And if you pass both of those, then that's the end of the assignment. So UART is not terribly complicated. And honestly, like once you get it set up and you can send and receive stuff, that's what you need to know. This is due Wednesday morning after 4th of July break. So I'm going to start talking about SPY on Monday when we get back. So we're going to continue talking about SPY on Wednesday. And we'll probably start having a SPY lab on the Wednesday after we get back. So you have like 2 weeks to do this thing, but if you come in here next Wednesday, you can bang this out in an hour and a half. That's it.
So you not have class next Wednesday?
You have no classes. So I have nothing planned for you except for you to come in and do this assignment. I felt like I've done enough to you guys already. So my plans have changed, so I will not be here next Wednesday, so you will not have class. You have this work to do. I have given you work. And you can come in here and you can knock it out in an hour. And I will be gone, but I'll be available over email. I'm going to be at a conference. Hopefully it's not boring. Hopefully there's good internet. So send me email. I'll get back to you. I will actually even take a board with me so I can grade your labs, and so I'll actually have something to work on. So you can send me your code. I can try it out, but I will be online. I will just not be physically present. Okay? Unless you want me to like give you a lecture from Salt Lake City over like Google Hangout. Nick's saying yes. Nick definitely wants that. Yeah. It'll be 7 in the morning. There won't be any coffee because everybody's Mormon, and it'll be pretty rough. So, this is what you got. I'm hoping to find some good coffee, I hope. This is what you got. Assignment 3. When we get back, so kind of looking at the semester, let me sort of show you the plan so we know where we're going. So if you look here, every topic I've sort of started on a Monday, and we finished on that Wednesday. So, this week we started on comms and UART. Today's our sort of review day. You've got your exam. What I've got for you is on the 27th, you're going to be working on assignment 3. When we come back, we're going to do SPY. This is actually going to get knocked down about a week because I need to talk about I2C. And I might switch those up because I2C and SPY are pretty hard, and I might loop this stuff in. But these are kind of the topics that we've got remaining. We've got SPY, we've got I2C, you've got ABC and DAX. We're going to talk about energy. We're going to talk about sleeping and energy modes. You can actually measure the impact of your code. We're going to touch a little bit on PCB design, enough that if you have to do that in Capstone, you're at least competent to do it. A lot of you pick this stuff up on your co-ops, and that's great. I'm going to talk about the tool chain, but you're going to have an exam when you get back in the middle, kind of in the middle of July, so the 18th, 15th, something like that. And then you'll have an exam on the last day. And I know it sucks to have it on the last day, but it's such a tight semester, it's the only place to put it. So the seniors will have already had their graduation dinners, and hopefully they're still with us enough to take the exam. So this is your schedule. We've got 1, 2, 3, 4, 5 more topics to get through. You're gonna have at least 2 more labs. Ice-Routine SPY, and I'll probably have a lab on PCB design, or at least another assignment. You'll end up having at a minimum 4, probably 5 labs. Questions on this? Questions on where you're going? Okay? No, because I changed it. When I know stuff, I'll put it up there. But I was going to be here until 2 weeks ago. So, once I know something, I'll put it up. All the lectures are available. So.